that, I'll send out an email discussing that after class today so that we can all remember when that is. And I'll have it posted on Moodle too, so you should be able to see that in a couple places. Okay, so what is going to be on the exam? Will be material up to and including the homework set that you're working on for this week. So the one that you're turning in on Thursday, the exam can cover stuff up to and including that. And really on that, I mean really the first two problems. Problem 3 is there's not going to be something specific to that on the homework. So right, it's going to be, what is that, Thursday? I can't remember my date now. 11? Thursday, March 11. So it will be 5 or 6 questions. 2 are going to be longer, and then 3 to 4 short. So, right, it's going to be, I would say, like from my perspective, I would expect the 2 longer questions to take about the same, like those to be about half of the exam each. Like 2 questions that are about half of the exam and 4 questions maybe that are the other half of the exam. It might be even a little bit like the 2 questions are 60% and the 4 questions are 40%. So there will be 2 more in-depth, more kind of higher order questions, and then a couple that are testing some of the more of the basics or like faster calculations. So the types of the kind of content that we cover, just as a reminder, so basic, conduction, convection, or radiation. So this could show up either in a separate question, like one of the short questions could be asking specifically about radiation, or it could show up like as part of a larger question where you have to know something about how conduction works or how radiation works in order to solve it. So this could be a standalone question or part of a larger thing, but those concepts for sure will show up. I mean, this is what we do each semester. One of the big questions will be something on thermal resistance, where you have to like make thermal resistors and calculate an equivalent resistance and calculate heat transfer. Maybe you have to calculate temperature like across one section of a larger thing. So you may have to do like, right, the equivalent of you have 3 resistors and you put voltage probes across one of them. Like what's the temperature drop across this one thermal resistance? Something with thermal resistance. And I would say it's a fair bet, and as the person making the exam, I have some control over this. It's a fair bet that that's going to be one of the longer questions, will be a thermal resistance type question. The other, the other main topic that we dealt with was the heat diffusion equation. So like conduction, when there was some thermal generation, Q dot. This would be another thing to be like, oh yeah, that was a big part of what we did. So there's probably going to be a longer question on something like that. Looking at maybe finding what the temperature profile is in a certain system, or finding the temperature at a certain location because you found, you know, something like, so there are a number of different things that I could ask, but that's going to be something else that, again, I think it would be fair to assume that those are going to be the two longer questions. One will be thermal resistance, one will be heat generation. The other possibility for that would be fins. Or extended surfaces, and really these three are are kind of the main bulk of what the exam is going to be. Right, those are the three things that we've spent the most time on so far. So within those three, definitely that's going to be the majority of the exam. The last part that may show up somewhere is the lumped capacitance model. Right, which is right, a problem that's not steady state. So you may be asked to do something like calculate the temperature at a specific time for something. You may be asked to, tell me something about how well the lumped capacitance model would work to describe a system, whether it would be a fairly good approximation or a bad approximation. You may be asked something about that, but again, I think that's not going to be a major part of the exam. We haven't done too much transient stuff. So most of that is going to, like the stuff that we're doing today and tomorrow and maybe the day after that, so that kind of stuff will be pushed to the next exam. So that won't be on this exam in a big way, although it might show up in one of the shorter questions. I think that's it as far as topics. What the exam is going to look like. So it'll be an hour-and-a-half exam. We will have, or hour and 20 minutes. So you'll have the full hour and 20 minutes. We do have a class in here after us, so we're not going to be able to go over that particularly long. But we'll have an hour and 20 minutes. If you end up for some reason, or if you're going to be taking it virtually, just reach out to me as soon as you know that, and we'll figure out a way for you to make that work for whatever your specific situation is. During the exam, we will have, I will give you a handout, and I'll post this on Moodle so that you can see what that looks like. But I'll give you a handout that has a lot of like standard unit conversion stuff. It has, stuff about like some charts that maybe you have to read to find fin efficiency for a goofy shaped thing, or so it'll be kind of like some of the basics, tables and charts that you would get from our book. I'll give you that as a handout that you can have with the exam. And then, like I said, I'll post that on Moodle so you can see it beforehand. And then during the exam, you'll have a one-page thing of notes, and you're welcome to use both sides, but like one thing, page of notes. So hopefully between those, I would focus, I'll try to give you some of the basic stuff, like tables of thermal resistance stuff and some of those basic things. So you'll hopefully not focus on having to write down every equation, but you can focus on, like on your sheet, how do I think about some of this stuff, and kind of more conceptual things. So I'll try to give you a lot of the basic equation type information for some of this stuff. And if there's something specific that you think I should give you, like a specific table, and I don't, I mean, you can ask me. It could be that I just forgot. But any questions? Yeah, Rachel?
So we just like wrote the stuff for it, and we didn't have to solve anything? Would that be different on this exam if we have to solve for something?
Yeah, so the question was, for the last quiz, we just solved, like, we didn't solve the heat diffusion equation, we just simplified it and gave it boundary conditions. I think it would be, you could expect on the exam to do something where you have to actually go through and get a temperature profile based on the heat diffusion equation. I would say still, from my perspective, like a major portion of the grade for whatever, if that were a problem, the major portion of the grade would be, did you set it up right? And did you simplify it right? And did you get the boundary conditions correct? If you screwed up, like you integrated, you know, something squared and you said it was something to the first power because you accidentally took a differential instead of an integral, like I don't care that much. But so most of the problem would still be, did you set it up right? Did you use your solution to answer whatever specific question there was or something like that? Okay, anything else? All right, cool. So what are we doing today? So what we did last time is we found, we're looking at what we call semi-infinite solids. And looking at, so if we have something that's, we are looking at these two extremes first. If we have something that's infinitely thin, it's all at a one constant temperature and it all changes evenly. If we have something that's infinitely thick, it changes just at the surface, and far away from the surface, nothing changes. So those are going to be our two extremes. And then obviously, like there's going to be a middle ground where the surface and the middle are both changing together, and we'll have to deal with that separately. But we want to first start with these two extremes, something that's infinitely thin, then something that's infinitely thick. So the whole thing is changing at one temperature or just the surface is changing. So a semi-infinite solid, we looked at this equation, right? 1 over alpha, d temperature, d time was d squared temperature, dx squared. We introduced this weird thing. We said let eta be defined as x over square root of 4 alpha t. So this is our similarity variable. And then we spent a little time reordering our differential equation based on the fact that we have this thing, this new thing eta. So we said, okay, so how can I express d temperature, d time in terms of this weird variable eta? How can I express d temperature, d squared temperature, dx squared in terms of this goofy thing called eta? And what we ended up with, I'll put a magic arrow. We're going to basically take our previous partial differential, right? It's a second order partial differential, in terms of this similarity variable. And this is where we ended last time, if I'm not mistaken. The temperature, the eta, the squared temperature, the eta squared. Right, this is where we ended last time, I believe. So the reason that we went through all of that work to try to transform the differential equation is because we went from something up here where temperature varies both with time and with space, to something over here where temperature only varies with this similarity variable eta. So kind of the weird thing about this is it's not like if you have something that is infinitely thick and just the surface is changing temperature. The kind of weird insight is that, right, that time and space are going to be kind of linked. And we'll see when we look at solutions to this, I think you'll see what that actually looks like. The same thing happens, and we'll see a little bit, right? If we want to solve this differential equation, we have to have two boundary conditions. We had in our original problem an initial condition and two boundary conditions. So kind of the weird thing is we have to transform our initial condition and two boundary conditions into two boundary conditions kind of in terms of eta. So our initial condition was everything's at a uniform temperature. So at T equals 0, T is T initial. Our boundary condition was at x equals 0. So that would be at the surface. Something happened. We actually didn't define what was happening at the surface. I'll do that here in a second. Our second boundary condition, though, was at x equal infinity. And that was that the temperature at infinity was never changing. We're going to, because it will make our lives easier when we solve this, we're going to say that at the surface, the temperature is just a known temperature. Okay, so it's a constant temperature. So, right, what's happening, we have this really big slab of something, and we smack something on the surface, and at time 0, the surface is a certain temperature, and then we're going to be watching how heat kind of moves into that object and changes the temperature. Okay. So now we can rewrite our boundary conditions in terms of eta, right, where this equals, let's just to remind ourselves, this equals x over square root 4 alpha t. So if we had a boundary condition at x equals 0, at x equals 0, that's going to be eta equals 0, because we have a 0 on top, so that'll make the whole thing go to 0. So at x equals 0, so our first boundary condition is going to be that temperature eta, evaluated at eta equals 0, equals the surface temperature. And at x equals infinity, Eta goes to infinity because we have an infinity on top. And at t equals 0, eta equals infinity. So this is how we kind of mash our two boundary conditions into one. So we're saying that really far away from the surface, nothing had changed. So the initial condition and really far away from the surface are the same thing. Right? Does that kind of make sense physically why that would be? Because we're kind of defining this as something that really far away, it's still at the initial condition. It hasn't changed. So time 0 where nothing's changed or really far away, they're the same thing. So this would be our second boundary condition. Temperature beta as eta goes to infinity equals the initial temperature. So now we have our boundary conditions. We have a second order differential. Now we can just solve it. And it's actually relatively easy to solve now, which is nice. That's why we went through all the hassle of getting it in terms of this weird similarity variable. So we have now minus 2 eta d temperature d eta d squared t d eta squared. So just for the sake of simplifying things, let's call d temperature d eta g. Or you could call it t prime or something like that. I don't know. It's going to be some other function. We'll call it g. So then we have minus 2 eta g equals d g d eta. Then we can separate variables and integrate. Right. So we have minus 2 eta d eta equals 1 over g dg, and then integrate. So this gives us minus eta squared equals the natural log of g plus c. Okay, or we can write, if we want to, so natural log of g equals minus eta squared. I guess it would be still plus c because it's a different c. So g equals e to the minus eta squared plus c, which equals e to the minus squared e to the c. Or we'll call it c1 e to the minus eta squared. All right, and then we can do kind of the same thing. So now we have g, which is equal to just d temperature d eta, equals c1 e to the minus eta squared. We can separate variables on that and then integrate. And this gives us c1 to the minus eta squared d eta. Then we integrate. We're going to be integrating from 0 to eta. And this gives us temperature equals c1 times the integral from 0 to eta of e to the minus eta squared d eta plus C2. Okay, and that integral is going to be something. If you're really fancy, you can just look at it and know what the answer is, right? If you teach calculus or something, you say, I've seen that integral before. It's right. We run in heat transfer. We run into a lot of weird integrals that just happen to be functions that, like, if you knew what it was, you'd say, oh, there's a Bessel function, or there's the hyperbolic sine, or there, so we run into some weird functions sometimes in this class. This is one of them. This is the error function. So ERF of eta, and if you plug in your calculator ERF, you ever heard of ERF? It's a fun one to say. So if you plug in ERF of some value on your calculator, it will do the error function. What it's doing is this integral. The error function is 2 over square root pi times the integral from 0 to eta. This is the definition. Minus u squared du is defined as the ERF of eta. So this is the definition. You don't need to really remember that. Specifically, we'll look at what the error function is. You can see it's kind of ish like an exponential, maybe. It's kind of ish like an exponential. It's just a function. It's going to be a function that decreases with as we go from 0 to infinity. It's going to look kind of have a decay similar-ish to an exponential decay. It's just a little bit different. This is the so the Gaussian error function, that's the definition of it. Okay, so it's a function called ERF. So then we can say that our solution, right? Sometimes it's handy to know just like, oh, I can see it and there's the answer. We can kind of absorb the 2 over root pi into our constant C1. The C1 is just a constant, so it can be a constant with the 2 over root pi in it. So that kind of gets subsumed into C1. So we get, this is C1 ERF of eta plus C2. And then we can use our boundary conditions. So our first boundary condition is at 0. Right, this is at the surface. T equals Ts. So the error function of 0 is equal to 0. So this gives us T equals C1 times 0 plus C2. Yes. Which tells us that C2 equals the surface temp. And then at eta equals infinity, which is our initial condition for far from surface. right? It's both of those things. T equals T initial. And this one, you have to know something again about the error function. So this is T initial equals C1 Earth infinity plus TS. So Ti minus Ts equals C1 Earth infinity. And it just so happens that the error function of infinity is 1. So this tells us that C1 equals T initial minus T surface. Okay, so our equation, so we still have it in terms of this thing, the error function. We can write it in a different form. We could write it T minus TS divided by T initial minus TS is equal to the error function. That would be our equation. Or we could write it in terms of our actual variables, space and time. Ti minus TS equals the error function of the x over square root 4 alpha t. And this would be kind of the more useful way to write it. But you see, from this equation, it's not really one of the variables, time or space, that matters. It's this goofy looking combination of time, space, and thermal diffusivity. And those three things together in this weird kind of thing, those are what actually control our temperature profiles. So we get, just to kind of bring it to an analogy to the stuff that we just did, we have for a semi-infinite solid, okay, so this, if the Fourier number is less than about 0.2, right, where the Fourier number is equal to alpha t over L squared, right? This is our dimensionless time variable, because we can think of something being semi-infinite when we're looking at like just the first few moments after something happened. So this is a good model when that's true. And then we have to know for semi-infinite solid, we have to know something about boundary conditions. If t evaluated at x equals 0 is T surface, then we have, right, just another way to write the equation above, x over 4 square root 4 alpha t. Okay, so if we're looking at short enough times, we can approximate things as a semi-infinite solid. This would be a relatively easy model for that. For the lumped capacitance, For the lumped capacitance to work, we said we had to have the BO number less than about 0.1. Again, neither of these things are hard and fast rules. They're both just approximations for when these are going to be most useful. The BO number is HLC over K. And this one, for both of these systems, the L is the this critical length. Like what's the length scale that's the most important? So if you have a wall that like heat's coming in from both sides, it doesn't have to go all the way through. It only has to go halfway through. So it's the volume over the surface area is this critical length. So it's going to be different if you have a cylindrical thing, heat's coming in from all sides, so it doesn't have to go like the full radius. It's volume over surface area. Lumped capacitance, this gives us, I don't know why that turned to blue. This gives us that same ratio is the exponential of minus, right, ASHC over rho VCP times T. Right, so the semi-infinite solid, an infinitely thick thing. The lumped capacitance, an infinitely thin thing. They both have a relatively similar form, and we're going to see this. If you've started on the homework, you're going to see this more, where we don't really care about the absolute temperature differences. We typically don't even care specifically about like the exact time. Really what we care about is for all of these things, we have specific ratios of properties and specific ratios of things that are actually the important things. So, right, we don't care specifically about the surface temperature and the temperature initial. We care about what is the ratio of the temperature differences initially and finally. So that's what matters. It's not temperature specifically. It's always temperature difference. It's not, right, in the lumped capacitance model, it's not time specifically and like heat capacity and thermal or convection. It's not like all of these things individually. It's only specific groupings of variables. So I think we can see that in both of these two solutions. But that's something that's going to be cropping up in more and more as we go on through heat transfer. It's almost in all of these cases, it's never like a single variable that matters. It's always specific groupings of variables. And as long as you have like the same grouping of variables has the same number, that's what actually matters physically. Which is kind of a weird concept because I feel like in normal life, we don't typically think of things like that. We think of like, you know, thing A and thing B, they're different in 5 different ways, so they can't be the same. But a lot of times they'll collapse to the exact same mathematical behavior, which is interesting. So we'll continue to look at that. That's just something to point out now. But let's look at an example. So just to get a sense of what this looks like. So we have this is going to be similar-ish to the problem that you guys solved on the in-class thing where we used the lumped capacitance model. We're just going to look at it and say, what happens right at the beginning? How are things changing? So we have a steel part of thickness 2L equals 6 millimeters. We're doing that because it's like a rectangular part. quenched in oil. So we have some initial conditions. Initially, the steel is 500 C. And the oil is 100 Celsius. And we'll plot the temperature profile over the first few moments. So we'll plot a couple temperature profiles in this really initial time thing when it's still acting as a semi-infinite solid. So the fun part about this is, right, our model is theta over, sorry, getting that messed up. Theta over theta I equals Earth X over 2, sorry, I'll write it the same, 4 alpha T, if TS, or sorry, if T at X equals 0 equals TS. So that's our model only in the case of that specific boundary condition. So we have convection at the surface. And this is why you'll see very quickly why we didn't actually solve this. So with convection boundary condition, so right, that would be minus K at d temperature d x evaluated at x equals 0 equals HC T minus T infinity. We would throw something like that in at the boundary condition, and out would pop. I'm not even going to try to go through and do it, but it would be, oh boy, T minus T initial over T infinity minus T initial. So the same kind of ratio of temperatures. This equals Earth C, so we get an even more fun Earth version. Earth C of X equals 1 minus Earth of X. It's called the complementary error function. You can't actually do it in your calculator if you just type in Earth C, but you probably have to use like the letter functions to actually do it. So it's kind of a weird one that like you don't have a, I would doubt you have a pre-built button where you'd be like second Earth C. I don't know, maybe some fancy calculators have that. Mine certainly doesn't. You get that, Earth C of X over square root 4 alpha T. So kind of the same. Minus, and this is a big one, exponential of hx over k plus h squared alpha t over k squared times, I'm going to run out of space here. It gets ugly. This is why we didn't do this. Earth C x over square root 4 alpha t plus h square root alpha t over K. So you get this big ugly thing. So you can see why this wouldn't have been fun to derive. But you can also see a lot of the same, right? It's the same kind of garbage that happened when we tried to use convection as a boundary condition before. Like we had for fins, for example, if we used an insulated tip, then our equation was fairly straightforward. When we used convection, then we didn't actually derive it, but there was this huge, big, ugly thing that had some similarities. It still had like cinch and cosh, but it all of a sudden had like lots of extra cinches and coaches with M's and L's and other garbage. So this is the same kind of thing. So it still is based off of the error function. It still has this eta term, right? X over 4 alpha t. You see that pop up again and again, but it also has a whole bunch of extra garbage. So there's a lot of similarity, but it's also like a little bit of extra complication. So we would have to then, like, this gives us the temperature profile at every time. So what we're going to do is thankfully use my pre-built Excel spreadsheet because I don't trust myself to enter that on the fly and actually do it correctly. So let me flip this around so I can use Excel. But I think it's instructive to look at what happened. Okay, so I have this pre-built spreadsheet. So I have a graph. We have a couple properties for this problem. So I can zoom in a little bit. So we have alpha, just a number, our initial temperature, our initial temperature, the temperature of the oil, 100. And then I gave values for H and K. Based on the H I made up, K is for steel. So what I did, I have a column of X in millimeters. So our bar was a thickness of 6 millimeters. So we're going to look at just the half thickness, right? Because it's going to be a mirror image on the other side. So we'll define about an x-axis that goes every 0.2 millimeters up to 3 millimeters. And then I just made a separate column next to it that throws that into meters. So this is my x-axis in meters, from the surface at 0 to the center of the bar at 3. Our initial condition is that it's 500 everywhere, so I'll just write, copy that. And you can, one of the magic things in Excel that you maybe don't know yet, but if you don't, you should learn it. When I copy this, there's the little like box in the lower right-hand corner. If you double click it, it will copy down to the end of whatever the adjacent column is, which makes it super happy. So you can see there, okay, there's my plot. The initial temperature is 500, so it's a flat line. Super exciting. Then what I have entered in this cell, and this is where the magic happens, you can see my wonderful equation. So look at how many parentheses are correctly applied in that. I give myself an A for that equation. I've saved this for and I will continue to use this equation for a long time because otherwise I will never get it right again. Okay, but all it is that equation that we just wrote down. You just have to make sure your parentheses are right. And what I did is I went in and locked all of the cells, like all of these top constants are locked with the double dollar sign. The X dimension here is the purple. So that's locked. I don't know, it's kind of hard to see, but that's locked with a single dollar sign just on the column. So when I drag this down, the X will drag down with me. And the time is up here, the time in seconds. That's locked with a single dollar sign. So if I drag that to the right, it'll drag to the right with me. So if I drag down, X will go down. If I drag to the right, that will work too. So again, I can take this and I can just double click and it will drop down. You can see I maybe didn't choose a nice enough X-axis because it looks like a little bit jagged. So let me make that a little bit better. Instead of 0.2, let's use 0.02 because it's easy enough. So we'll drag this down all the way to 3. To get a little bit smoother curve. Okay, so there's the center, and this is where it's really nice not to have to copy everything. So this is okay. So you can see at this time, this is 1/1000th of a second after being submerged in the oil. The surface has dropped by about 5 degrees, but just a little ways away from the surface, you're still at 500, right? A quarter of a millimeter from the surface, you're basically exact, like nothing has changed. We can do the same thing. We can drag this over here, copy those down, and see what happens. And you can maybe start to see why this similarity solution actually worked just visually from this. So as we go from right as we drop this thing into the oil, we get the same shape curve every time. It's just that like the temperature is kind of, continually moving in, but the curve is staying the same shape, right? The red curve, the gray curve, the yellow curve, they all look exactly the same, really. It's just like the heat is slowly moving into the solid. But they all have this same, you can see it's kind of an exponential-like shape. It's not an exponential, it's a whole big ugly equation with error functions and complementary error functions and stuff, but it's kind of a similar type of decay. And you can see that in all of these cases, the temperature really far away at the center is still unchanged. So we're still stuck at 500 here at the center. If we changed the time to, I don't know, 5, 1, yeah, something like that, like 1 second. The model is still going to give us answers, right? It's going to tell us that this is what the temperature profile looks like, but our fundamental assumption behind the model broke down. Our fundamental assumption is that the temperature far away from the surface is unchanged. This is predicting that the temperature in the middle drops to 480. We said, like, the whole basis of our model is that didn't happen. So if that starts to happen, that's when this model breaks down and starts to give garbage. So it will still give you answers, but your answers stop mattering, basically. So those stop actually being relevant. They stop mattering. They start being just garbage. So that's one of the things with both the lump capacitance and the semi-infinite solid. It can give you valuable information, but you have to understand what are the limits of the models, because they'll spit out numbers no matter whether they apply or whether they don't apply. They'll still give you answers. But right, what this would predict, again, this is going to be a mirror image of the other side. What this answer predicts, the green line, it's going to predict that there's a pretty sharp point, like a sharp discontinuity in temperature at the center, which we know kind of by physics, like that's not going to happen. There's going to be a smooth curve at the center, and there's going to be a spot at the center where the derivative is equal to 0. The model doesn't predict that because we're now outside of the bounds where it actually is true and valuable. Okay. All right, so we'll leave that there. So I'm going to put that on Moodle so that we can all have that. And then we'll look at just one other case that I think is interesting, kind of specifically interesting for the semi-infinite solid model and where it can be useful to use this. Okay. So in a lot of situations, quite regularly, there are systems where one thing comes into contact with another, like two things are at different temperatures and they come into contact and then things start to happen. And a lot of times we want to understand sometimes the long effects, like what happens a long time from then, but a lot of times we care about what's happening like relatively early on after these two things come into contact. So if you remember from the first day of class, there was this space shuttle heat tile, like a thermal insulation tile that they took out of a 2000 degree Celsius oven, and then somebody picked it up with their hands. You remember that? So what's happening in that situation is it's two things that are initially at the spaceship tile is initially at like 2000, and your hand is initially at your hand temperature, like 37. And these two things are coming to contact, right? Coming into contact with each other. And what keeps you from burning is the first, little bit after your hand comes into contact with this space shuttle tile, right? How much does your hand actually heat up? How much does your hand cool down the spaceship tile thing? How does heat flow between you and the tile? But a lot of times, like the very first moments of these two things interacting, both of them were initially at two very different temperatures. They're coming into contact, and then things are starting to happen. So we'll look at using this model to be able to describe systems like that. You'll actually look at that specific example as a homework problem, which I think will be kind of fun, but that won't be for a little while. So I won't wreck it by doing it as an example in class. You'll do that kind of more fun one as a homework and see exactly how that system actually works. But we'll do a different one. I would guess living in Holland, I know it's cold out, but we have all experienced this. So here is sand. There is your foot. Has anybody ever stepped on hot sand and burned their foot? I certainly have. So we can treat, when you first take your first step onto hot sand, you can treat both your foot, the bottom of your foot, and the sand as semi-infinite solids, right? They're both at some initial temperature, and the first little bit after you step on them, like the main part of your foot has, like the insides of your foot haven't heated up significantly. The sand far away from your foot hasn't really cooled down, but they're coming into contact. Your foot temperature is going up, like in the first couple layers of skin. And if it goes up too high, you burn yourself and start running around like a little child, right? This is what I do. Okay, so we can think of both, treat both foot and sand as semi-infinite solids when they first come into contact. We're going to call, for the sake of variables, rather than foot and sand, we'll call your foot A, and the sand we'll call B. Just some thermal properties of things. We know that your foot and sand, we know that the initial temperature of your foot is about 37. We'll say it's a relatively hot day, but not scorching. The sand is about 60 degrees Celsius, right, which is hot, but not wildly so. Those are conditions you could find at the state park. Not today, but some days. The thermal conductivity, 0.3 watts per meter Kelvin. This one's a little bit tricky for human bodies to actually get accurate values because it does change based on water content in your skin, and your body has changing thermal conductivity as you go further into yourself, right? The first layer of skin, like further into the more of your meat, it's going to have a little bit different properties. So your body's not quite this easy to model, but we'll assume it's just constant thermal conductivity. Same with density. Your body is not uniform density, but we'll pretend it is. We'll pretend it's water. You're mostly water. So 1,000 kilograms per meter cubed, and same idea with heat capacity. 2,000 joules per kilogram Kelvin. So these are ballpark, relatively accurate, but not going to be the most sophisticated model for your body, but it will give us some understanding of how this stuff works. So that's your foot. For sand, would be 0.27 watts per meter Kelvin. The density, about 1515 kilograms per meter cubed, and a heat capacity of 800 joules per kilogram Kelvin. So largely similar properties, but different heat capacities. They're like more than a factor of 2 different. So what's going to happen when you first step on the sand? When they first contact, the surfaces reach thermal equilibrium. Thermal, M. Okay, so right, the TAS equals TBS equals T surface. So this is, right, when 2 things come into contact, there's going to be a flow of heat in between them until the temperature becomes constant. And if you look at just like the very, very surface, right, the surface couple atoms, that's going to happen really quickly. Almost instantaneously. It's not instantaneous, but it's going to be pretty close to instantaneous. We're just at the very first few surface atoms on each thing reach thermal equilibrium. So that's what we're talking about. So really quickly, not instantaneously, but really, really quickly, those surfaces are going to match temperature. Now, just a little ways away from the surface, nothing has changed yet. That takes a while, but the surface is going to be really quick. So the second thing that we can note is that, okay, so heat is going to be flowing from the sand into your foot. And the first law of thermo says that the heat that leaves the sand is the same as the heat that goes into your foot. Those 2 things have to be equal. So Q double prime of your foot at the surface, or I'll use our notation A so I don't have to keep writing foot. Q A surface is equal to Q double prime B at the surface. So by the first law of thermal. So we could write what the heat transfer is. So this would be equation 5.61 tells us that Q double prime of A at all times. So this is just the Q version of our error function, right? So we're going to be taking the, how do you find Q? Q is minus K dt dx. How do we find dt dx? Well, we take the differential of our error function with respect to x. So that's all that this is. So this is equal to Ka Ts minus T infinity A over square root of pi alpha A T. That's all under the square root. Okay, and we could write QB equals the same thing. QB equals KB Ts minus T initial B square root of pi alpha B T. So those two things are equal. So what we can do is just set them equal to each other. So Ka initial A over square root pi alpha A T must be equal to KB right. This would be just that energy balance that we talked about. This is just that energy balance, and then we could find this and thanks. I'm not going to do all of the algebra, but we could take this and we could solve for the surface temperature, right? We could solve both of these for the surface temperature fairly easily. Not going to be super easy, but it'd be fairly easily. Okay, we'd have to multiply through by K, and then we'd have to get everything on the same side, and we'd have to do some algebra. Solve. And we could get that the surface temperature would be equal to T initial K rho Cp. So I'm going to write the notation like this, so I don't have to put an A next to all of those things. So it'd be T initial A times Ka times rho A times Cp A. Let's say all of that has an A subscript. All of that is for your foot. Plus T initial K rho Cp. All of that has a B subscript. Divided by, what am I doing? K rho Cp of A plus K rho Cp for material B. Okay, and this is kind of a cool equation because what this tells us, right, this is really just a weighted average, right? So what we would expect is if the two things have the exact same properties, when we brought them together, the surface would be at the midpoint of those two temperatures, right? If one is 100 and one is 0, and they're the same thing, and we bring them together, we would expect the surface to get to 50. That's all that's happening, except that the surface is getting to some weighted average because these two things have different properties. So this is a weighted average with the square root of K rho Cp as the weight. So that collection of properties, heat capacity and density, those two things make sense because that's like how much heat is in the material. And then thermal conductivity because that, right, that relates to like how fast heat can actually get to the surface. So if you have something with that like holds very little heat, it's going to contribute less than something that holds a lot of heat like water, which I think makes intuitive sense. But the kind of interesting, it is just a weighted average between the two temperatures, weighted by the specific weighting factor, which is a function of what the material properties are. Okay. So if we wanted to continue on, and I think we'll stop there because otherwise it'll take us a little bit. We're not going to finish this problem anyway, and this is a good place to stop. But if we wanted to continue on, what we're going to do next is, okay, find what that surface temperature is initially, and then we can use some of our models to see how heat then will go into your foot before it burns you. Like how long will it take for heat to actually start to diffuse deeper and deeper into your foot? Because you don't burn if the very first, like the surface of your skin gets to a high temperature, right? You burn when you get like a couple layers of skin deep. So we'll watch how that happens as we burn our foot on the sand. But I hope you guys have a good Tuesday. I'll send out an email reminder that the exam is a week from Thursday. But there's a homework due Thursday, help session tomorrow. So try to take advantage of that. Otherwise, have a good and happy Tuesday.